in this video we are going to see about the design of bell crank lever. Okay, as we have started with the design of levers, so we have seen in previous video about the numerical and design procedure for hand lever. Now in this video we are going to see how to design bell crank lever. Please see guys, what do you know bell crank lever is? See, in a bell crank lever, two arms of the lever are at right angles. See guys, we are going to see it in detail in the diagram. So in bell crank lever, two arms are at the right angles with each other. Okay. Then such type of lever is used in railway signaling. See guys, such type of lever is used in what? Railway signaling, Hartnell governors, and drive for air pump of condensers. Okay, these are the various applications of bell crank lever, that is railway signaling, Hartnell governors, and drive for air pump condensers. The arms of lever may be rectangular, elliptical, or L section. The arms which are inclined at right angles with each other, it may be rectangular in shape, elliptical, or L section. Now let us see what is next. And this is the diagram of bell crank lever. Please see here, you can easily this bell crank lever diagram. You can see here these are the two arms. This is what effort arm. Please see, this is effort arm, and this is what load arm. Please see, this is horizontal is your load arm, and this is what effort arm. And these two arms, that is effort arm and load arm, are have right angle, are inclined at right angle. That is, it makes angle of 90 degree with each other. This is exactly 90 degree. So this is boss, this is fulcrum, you can see, and this is L2, that is load arm, and this is uh, effort arm, and this is load arm L1. Okay, this is W, that is load, and this is P, that is effort. And this is width of the your load arm, and this is thickness of your load arm. Okay, so all this is about the bell crank lever, how it is you know assembled. That is this is effort arm, this is load arm, and which is inclined at right angle. And we are going to see more detail about this in next slide. Let's see. Now see guys, this is, let me focus your attention over here. This, see guys, this is the bell crank lever. As you are seeing here, this is bell crank lever. Please try to understand how it is constructed. This is RF. You can see this force RF is given here. RF means nothing but your reaction force. What it stands for? RF stands for reaction force. And this is what this green color rod type structure called as fulcrum pin. See guys, it is called as fulcrum pin. This is what? This is load arm, and this is effort arm. This arm is your effort arm, and this is your load arm. This F is your load, and this P is your effort. This RF is your reaction force, and this is what? Bushes for turning purpose. Okay, this is what? Fulcrum pin. We know that we have seen fulcrum theory portion in previous videos. So we know that your lever, whether it is bell crank lever, hand lever, or foot lever, your lever is going to turn about a fixed point, which is called as fulcrum, that we know. So your lever is going to turn about a fixed point, which is called as fulcrum. This is fulcrum pin, and this is what? Reaction force. So we need, while designing a bell crank lever, we need to calculate this reaction force first, because your uh, bell crank lever has two arms, that is load and effort arm, and that which makes an angle 90 degree with each other. And we need to calculate this reaction force first, so that this is the bush. So we need to design this portion. Okay, so how we are starting this design of this bell crank lever? By calculating this reaction force. Okay, so if you see, if you understood this, what I am trying to tell you, so this is what? This is fulcrum pin, about which your load arm and effort arm is going to be turned for bell crank lever. This load and effort arm makes an angle of 90 degree with each other. This is bush along with your around which your lever is turning, and this is fulcrum pin, which is fixed point. And by this fixed point, we need to calculate first reaction force. This is the first step to solve the design problem regarding bell crank lever. Okay, now what it is written here, please see, design considerations of bell crank lever. Now while designing bell crank lever, what we need to consider? Please see, reaction force at fulcrum. This is first step, I have told you earlier. First step is reaction force at fulcrum. We need to calculate this reaction force first. Then fulcrum pin, then we need to design this fulcrum pin, which is shown by green color. And third is design of lever. Okay, we need to design the overall lever. Okay, so this is about the details of bell crank lever. And next is now images of bell crank lever, where it is used. Okay, if you see this image, this is the real image of bell crank lever, how it looks like. and this is also bell crank, which is a moving part, which is moving pivot. This is fixed pivot, we can call it fulcrum, and this is moving pivot, and this is moving pivot. About this point, this your bell crank is going to be turned like this. If you see my cursor like this, okay. Then what next? So these are the applications of bell crank lever, which is used in what push rod mechanism, and which is used in Hartnell governor. This is Hartnell governor diagram, and this is push rod mechanism. So this bell crank lever is used over here. Okay, these are bell crank lever. Please see, these are the bell crank lever here mentioned here, bell crank lever. Okay. The next is, now we are going to start actual design procedure of bell crank lever. Please see. So this is the design procedure of bell crank lever. Please see what is step one. Step number one is calculate the reaction at fulcrum RF. See, that is reaction force. So calculate the reaction force. That is at, this is the first step. So RF is equals to under root of W square plus P square. See guys, RF is, how to find RF, that is, which is equals to W square plus P square. Note, to calculate W and P, if one of them is given, take moments about fulcrum. See guys, how to calculate this W and P? If one of them of W and P is given to us, then we need to take moment about one of them. Okay, so in this way we can calculate the value of RF. The next step is, step number two have some more step, that is design of fulcrum pin. Okay, design of fulcrum pin. This is step number two. Please see, A is, let D is equal to diameter of fulcrum pin and small l is equals to length of fulcrum pin. We need to consider small d as a diameter of fulcrum pin and small l as a length of fulcrum pin. After that, considering the fulcrum pin in bearing, we know that the load on fulcrum pin is RF. Okay, so bearing pressure is equals to load upon bearing area is equals to RF upon L into D. So is equals to RF upon 1.25 times D into small d. So that is why we need to assume small l is equals to 1.25 times of D. So this, keep this thing in your mind, that is, always we need to consider the small l is equals to 1.25 times of D. Then B step is checking shear stress induced in the fulcrum pin, as the pin is in double shear. Okay, we need to check shear stress induced in the fulcrum pin. So tau is equals to RF divided by twice of pi by 4 into D square. And what is step number C? That is, a brass bush of 3 mm thickness is pressed into boss of fulcrum as bearing. So always we need consider this brass bush of 3 mm thickness, which is pressed into the boss of fulcrum as bearing. Then therefore diameter of hole in the lever D is equals to D plus 2 into 3. Therefore diameter of boss at fulcrum is equals to twice D. So this is about the step number 2, this is design of fulcrum pin. What next? This is step number 3, that is design of pin at A. This is point A. Okay. So checking whether the effort at A is close to the value of RF, and if it is, take same dimensions for the pin at A as fulcrum pin. Please see guys what it is written here. Checking whether the effort at A is close to the value of RF. If your effort value is close to the value of RF, then if it is so, then take same dimensions for pin at A as fulcrum pin. Okay, so we need to take that same dimensions as at fulcrum pin. So D1 is equals to diameter of pin at A is equals to D, and 11 is equals to length of pin at A is equals to 1.2 times 25 times of D1. Then next is step number 4, that is design of pin at B. Let D2 is equals to diameter of pin at B and L2 is equals to length of pin at B. Similarly, we have taken for point A. Okay, so A is considering the bearing of pin at B. So we know that the load of pin at B is W. So PB is equals to W by D2 into L2. So assume L2 is equals to 1.25 times of D2, as we have assumed L1 is equals to 1.2 times of D1. Okay. So from here we can find D2 and L2 values. Okay. Then next, what see? Please see. This is also step number 4. B. Checking the pin for shear stress. As just follow same sequence as we have calculated for point A. So pin is in double shear we have considered. So tau is equals to W by 2 into pi by 4 into D2 square. And what see, as end B is fork end, thickness of each eye, that is T1 is equals to L2 by 2, and inner diameter of each eye is equals to D2 plus 2 into 3, where chilled phosphor bronze bush of 3 mm thickness is provided in each eye. So outer diameter of each eye is equals to capital D is equals to twice into D2. So see guys, these are the step number 4 for design of bell crank lever. Then this is the step number 5, that is design of lever. Considering capital T is equals to thickness of lever at section YY and B is equals to width of lever at section YY. So taking distance A from center of fulcrum to YY, maximum bending moment at yy is equals to w into L1 minus a, and section modulus is equals to 1 by 6 into t into b square is equals to 1 by 6 into t into 3t square. Assume b is equal to 3t. So value of b we need to assume 3t. Okay. Sigma b is equals to m by z. So I have just put all this value of m and z over here. So b is equals to w into L1 minus a, and this z is equals to 1 by 6 into t into 3t square. So we can find dimensions of lever b and t. Okay. So I think this is helpful for you.